All right, it is 2025, September 19th, approximately 8:33 a.m. We're going to be continuing along the exercises in Chapter 1 of Dummett and Foote with a special reference given to the Cola solutions, which, all of that is going to be linked in the description. We're going to be looking at so we're going to be looking at 1.5. So that's going to be all the stuff on the basics of the quaternion group, exercises on that. And I'm talking just to kind of stall myself so I can drink some coffee here. Coffee. Some interesting stories on the origins of coffee. I think it was like a bunch of knights saw that the Arabs had it. General term, right? No, but they went back to the Pope and they were like, okay, so we found this special sort of magic looking thing, and we think it's like from demons or something like that, The Pope takes a sip, and he's like, well, this is so good, we should spite the devil and bless it. And so he does. So that's an interesting story about coffee there. There's like there's whole books on like the history of coffee, and that's just a little snippet of that. But yeah, coffee, caffeine, it's like that stuff changed the Western world, changed the world. Okay, so anyway, back to the quaternion group, which is, by the way, not for nothing, that's a cool name. Just like say that you're looking at the quaternion group, and it just sounds a whole lot cooler than saying, oh, I'm looking at the symmetric group. It's like, oh, I don't care. But you say quaternion, it sounds like you're talking about something from another planet or something like that. Something out of a sci-fi novel. Yeah, okay. Back to the business of actually looking at these exercises. So for the first one here, we have compute the order of each element, of each of the elements in quaternion group 8. So Q sub 8, big Q sub 8. And so intuitively, how would you approach this? Well, the order of an element G is the smallest n greater than 0 with, G of n, G to the n, which is equal to 1, right? So negative 1 and, it's funny. I realized that I put hyphens in my notes, and so I said negative 1 first, but it's actually just 1. So 1 and negative 1, in this case, are scalars, so their orders are immediate. I, j, k, so I'm just kidding. Well, I, j, and k square to negative 1, so they need 4 powers to return to 1. Negatives of these cycles, negatives of these also cycle back to 1 in 4 steps. So let's take a look at that more rigorously. So by definition, Q sub 8, the quaternion group with 8 elements is equal to 1, negative 1, negative I, negative I, J, you guessed it, negative J, K, negative K, and I squared is equal to J squared, which is equal to K squared, which is equal to negative 1. I, J is equal to K. J, K, Rowling is equal to I. K, I is equal to J. Okay, so now that's what we have just by definition, just by the definition of what this thing is. So let's look at the identity. The identity and negative 1 first. Boopity boop. All right. So What's the order there? 1 is equal to 1 to the power of 1 is equal to 1, which implies that the order of 1 is equal to 1. And what's the order of -1? Well, whoops. -1 to the power of 2 is equal to 1, so the order of -1 is equal to 2, right? And now we erase the board to continue on with the rest of the exercise. Okay. So, negatives of I, j, k. So for these, so negative I, you square that, what do you get? Well, let's look at this. Well, this is actually equivalent to -1 squared times I squared, right? And that is actually equal to 1 times -1, which is equal to -1, right? So negative I to the fourth, so open parentheses negative I to the fourth, is equal to open parentheses -1 close parentheses squared to the second. I mean to the 4 to 4, and then yeah. So open parentheses negative I close parentheses to the power of 4 is equal to open parentheses -1 close parentheses to the power of 2, which is equal to 1. So the order of negative I is equal to 4. Okay. Now, the same sort of calculation, because of the fact that these things are equivalent, we have this neat thing where, by the same calculation, the order of negative j is equal to the order of negative k, which is equal to the order of negative I, which is equal to 4. So we've looked at all of those. We had that by the same calculation. So that's all of them, right? Let's see here. For the identity, we had that it was order 1. For -1, we had it was, the order of the identity was equal to 1. The order of -1 is equal to 2. The order of I, j, k, negative I, negative j, negative k, that's equal to 4. So we have, it's either going to be of order 2 or 4 in the quaternion group with 8 elements, okay? All right, well, we were told to compute the order of, not to say in general, but I mean, that is what it is, right? So, okay, so let's get into looking at exercise 2. For exercise 2, we have write out the group tables, the group tables for the symmetric group with 3 elements, the dihedral group with 8 elements, and the quaternion group with 8 elements, okay? So S sub 3, D sub 8, and Q sub 8. So list a convenient, okay. So let's just sort of like try and intuit around this. Well, what would we do? Well, it's like list a convenient generating set and a consistent element order, then fill the Cayley table by defining relations. Cayley table, group table, right? So for S sub 3, use transpositions in 3 cycles. For D sub 8, what we have is that, well, it's represented by, okay, how do I say this? By the elements of the group as well as the relations. So for D sub 8, we have R, and then we have S, such that R to the power 4 is equal to S squared, which is equal to 1. And then the, SRS, that's equal to R to the -1, we track how S flips powers of R there, and for Q sub 8, we use I squared is equal to J squared, which is equal to K squared, which is equal to -1, and IJ is equal to K, JK is equal to I, KI is equal to J, right? So let's get into looking at that a bit more rigorously, and in this case, we'll start out with, well, let's just go in sequential order, right? So we have S sub 3, which is equal to the set containing, well, it's more than a set containing, but let's look at its elements, right? So that's equal to this, okay, so we have here the elements 1, and then the cycle, open parentheses, 1, then 2, close cycle, and then we have the cycle 1, 3, close cycle, and then we have the cycle 2, 3, and then we have the cycle 1, 2, 3, close the cycle there, and then we have the cycle 1, 3, 2, close the cycle there, and that's pretty much it. So, well, no, that is it. So what then do we have left over? Well, how would we make the Cayley table for this, the group table for this? Well, let's get our elements up there. You know what? I'm going to do a little bit of a cheatsy maneuver and not make a separate table. I'm just going to use these elements as they are up here. Okay, so, and then I'm going to say, okay, how about this? How about I just kind of put this over here? 1, 3, 2, 3, 1, 2, 3, 1, 3, 2. Okay, now, and there's another mosquito just kind of flying around. I don't know. Gosh, that's so annoying. Okay. So for this top row, we have 1, the cycle 1, 2, and then we have the cycle 1, 3, then we have the cycle 2, 3, then we have the cycle 1, 2, 3, then we have cycle 1, 3, 2, right? So that's pretty straightforward, and so is this line here, right? Okay. Now, to fill this all out, it's interesting. You've got this sort of, no. Okay. Let me just fill this out row by row. So we get back to the identity here, and then for this here, what do we get? We have 1, 3, 2, then we have 1, 2, 3, then we have 2, 3, then we have 1, 3. Okay. Over here we have 1, 3. Let me see this. 1, 2, 1, 3, 1, 3. Then we have 1, 2, 3. Then we have 1. So there's this interesting diagonal that's going to show up here. So, okay. What's I going to say? Then we have 1, 3. Then we have, oh gosh. No. We have 1, 3, 2. We have 1, 3. 1, 3, 2. 1, 3, 2. Then we have 1, 2. Then we have 2, 3. Okay, and over here, I'm just gonna not waste too much of my energy by moving my hand back and forth. Okay, so this is 1, 2, 3. 1, 3, 2. Over here, that's 1, 3. 2, 3. 1, 2. 1, 3, 2. Is that right? 1, 3, 2, 3. 1, 2, 1, 3, 2. Oh, okay. Diagonal broken. Yeah, diagonal broken. Okay. All right, I can accept that. I don't like it. I should have swapped these around, but it's too late now. So if I wanted to keep the nice looking diagonal, but that's fine. I'm not going to rejigger these results to get the perfect aesthetic. So, all right. So there we go. There's the group table for 2 sub 3, right? So, like I mentioned earlier, we did this using transpositions in 3 cycles, okay? Now, let's take a look at this next one here, which is a dihedral group with 8 elements. All right. So D sub 8, let's look at the elements there. 1, R, R squared, R3, S, S, R, S, R squared, S, R cubed. And this is with the R to the 4 is equal to 1. S squared is equal to 1. SRS is equal to R to the negative 1, okay? Now, let's go ahead and look at our group table, right? So, oh, wait a second. Gosh, freaking dang it. Just realized those are the relations. I can't, can't do that. All right, so I'm gonna have to actually put in a bit more effort here and say 1 R, R squared, R cubed, S, SR, SR squared, SR cubed, right? No, SR not cubed, SR actually quite curvy. Right, rolls eyes, that sort of thing. It's okay, I'm here all day. Well, most all day. Okay, so this is side 1, R, R squared, R cubed, S, SR, SR squared, and SR cubed. They're not squared either, and they're still, all right. I am not going to have enough room to do this in a way which is aesthetically pleasing, I don't think. Just fine. You'll get the gist. And if not, I mean, like, my lecture notes are on GitHub, so, you know, you can look at that, and it's a lot more pretty than what I'm doing here. The point of, like, doing these lectures, it's like, well, it's a lecture. We've learned via lecture or, like, word of mouth and stuff like that for, like, as long as we've really been human, right? So this is more of a, what is it? What would you call it? Like, easier way to get to the memory nodes, I guess. It's a good little lecture notes make a good companion piece to the thing. So anyway, this is 1. Of course it is. So R squared, R cubed, S, SR, SR squared, SR cubed, SR squared, SR, oops, okay, SR, S, wait, hold on a minute, yeah, SR cubed, then 1, then R cubed, then R squared, then R, right? Okay. Let's just stick to this for now. This one's the easiest one. This is like the free spot on a bingo card, right? And you can just kind of, that's an identity right there, and then, ha, gotcha. Now I feel very accomplished, like a 5-year-old reading a chapter book that's actually, you know, that's actually like a picture book, but you don't want to take that accomplishment away from them because it's all they have for now. So you gotta let that grow, foster that. No, but anyway, parenting tips with no. So R squared and then R cubed, then 1, then R, SR squared, SR cubed, SR, R cubed, 1, R, R squared, then we have SR squared, SR cubed, S, then over here we have R, yeah, we have R squared, R cubed, 1, SR cubed, SR squared, SR. Then we have SR cubed. No, SR squared. I think it's SR squared that goes here because, yeah, SR squared. Now we have SR cubed. Okay, it looks like it's a male mosquito, and you can tell because of the legs, but if it gets any closer, I'll have to, yep. Okay, there we go. Anyway, where was I? SR cubed. This is more of the thing, right? It's not so much that it's difficult to wrap your head around, it's just it's difficult to keep track of all the little things. So SR cubed. Let me see. Should be, no, that's R cubed. So that should be, what, like S? Let me think. Yeah. SR1, R cubed, R squared, R cubed, 1, R squared, SR cubed. Fill this out via mumbling. No, but SR cubed, S squared, and then R cubed, then R squared, then R, then 1. Okay? So that's what we've got there. And that's our group table / Cayley table for D sub 8. Let's erase that and then get on to the last one here before moving on to the next exercise. Okay, so Q sub 8, quaternion group with 8 elements here. What is that? Well, we have the elements 1, -1. I mean, we looked at that before. -1, J, -J, K, -K. And this is with what? With what relation? I squared is equal to J squared. And I could try and like write along the side and then preserve this for the top bar, but whatever. And this is K squared. I don't really need it, so it's equal to -1. It's just more of a convenient sort of thing. Ij is equal to K. Jk is equal to lol, which is equal to I. Ki is equal to J. There we go. Right. It's supposed to be a 1. You were supposed to be a 1. And let's put that up there at the top. 1, -1. I, -I. J, -J. K, -K. Okay? It's just kind of always nervous whenever I start trying to do straight lines on a whiteboard because this could quickly go awry. There is not that many questions in this part. I thought there would at least be 4. Maybe I don't know. Maybe I just left one out of my notes. I'll check on that. Okay. So what do we have here? Right. Wait. Let me just. And then what's this? It's -1. Oh no. Okay. I, -I. Crud. No. Why do you spite me? Okay, so how about this? How about I just go, would that even work? I don't know. Okay, I'm just gonna leave negative k out because you know what? Gosh, freaking dang it. It really annoys me, man. Okay. Let's see here. Oh no, straight lines. They're going to destroy me. So, I, Claudius, negative I, J, negative J, bless you. Okay. Free, let's fill out the free spot on the bingo card right here, so. Negative J, K, negative K, and this one is, oh, would you look at that? That's just so easy. I'm invincible. Okay. I'm a genius. Just for, yeah, okay. 1, negative I, negative J, negative K, K. And then we have I, and this is negative I, negative 1, right? And then, what's this next one here? Where are we? Where am I? Who are you people? I, negative I, what is that? It's just 1, yeah. I, J, K, negative K, no, sorry. K, negative K, yeah, and then that should be J, that should be J, or negative K, actually, negative J, yeah, negative J, J. And if we look at that, we can just sort of look at this and see that it's mirror reflection. It's what is it? I don't know. There's not conjugate, maybe. I mean, it's just the negative of that. Like, it's just, okay, J, and, all right. Why I chose to do the script for one there, I don't know. It's just sort of a last check mark, I guess. And that's our Cayley table / group table for that. And each table follows by straightforward application of defining relations and closure, right? So that all goes quite swimmingly. Now let's move on to the last of the exercises, exercise 3, at least insofar as like my current set of notes are concerned. I could be wrong, like just, you know. I would carry around a big old copy of Dumb and Foot with me if, like, I don't know, that was at all practical. I mean, I guess, like, I'm mentioning it, I'm complaining about it. It's, like, it's practical enough to where, like, it would fill up that slot of complaints. But it's, like, it's a big book, man. And, like, I mean, relatively speaking, to a lot of books, it's a pretty big book, and I just don't have a lot of space in my backpack. I was thinking about, like, maybe I could get, like, one of those like, USBs that connect directly to the phone, and then, like, I could put the digital copy of Dumb and Foot, which I have, and then I could put, like, the digital copy on there, after I, like, scan it, right, but it's like $29 for one of those, like, around $30, so I'm thinking about it, I might, so... But for now, let's just look at exercise 3. So find a set of generators and relations. I did not have relations with that Q sub 8 there. No, but he did. Okay. Okay, find a set of generators. Oh my gosh, that's the phrase. That's the phrase. I'm sorry. Find a set of generators and relations which make up that makes up the what is it? Not the presentation. Is it the presentation or is it the representation? I think it's the presentation for Q sub 8, which is quaternion group with 8. So we are really focusing on this. It's almost as if the chapter is like named after it or something. This section, I mean to say. Okay, so intuitively, Q sub 8, well, that consists of these elements which are 1, -1, I, -I, J, -J, K, -K, those generators, right? Well, no. Those, so that whole thing is generated by I, J. I squared is equal to j squared, which is equal to -1, and ij is equal to k, right? So the element -1 is central and equals I squared, which is equal to j squared, which is equal to k squared. And we can encapsulate these behaviors as concise relations, which we do, but let's try and look at that a bit more rigorously, shall we? So how about this? For generator presentation. Yeah, presentation. So one valid presentation, which we've looked at, is this, well, we haven't looked at it in the way that we're looking at it now, which is, let me just preface this. One valid presentation is Q sub 8, which is equal to generators -1, I, J, K, with relations I squared is equal to j squared, which is equal to k squared, which is equal to ijk, which is equal to -1. And -1 is the central, right? So let's just make note of that. Yeah, okay. So here -1 is explicitly central, right? And ijk, which is equal to -1, that forces the standard multiplication rules. The standard multiplication rules. Multiplication rules. Sure, no. Ij is equal to k. Jk is equal to I. Oh boy, that's not good. Okay. So I'm just going to put like little bars instead of commas because my commas look like the j's. So, and ki is equal to j with ji equal to -k. And these are pretty cool because I guess it's like, you can look like, I think it's like particle spins. Don't quote me on that. Just talking out my bum there. But I mean, they remind me of like what I've heard people say about particle spins. So I guess, just like take that for what it is. But, okay. I guess that's why it's kind of like sci-fi-esque to me, quaternion. Even though it's just like 4 eon is basically what you're saying whenever you say quaternion, right? But now let's look at another such presentation, which is like the 2 generator presentation, right? So let's get to that, and we'll call it for 1.5. 1.5, that's not a lot of questions for 1.5, which I'm not complaining. At least for now. Probably have to look into getting more. So a minimal 2 generator presentation. So how about this? Setting x is equal to I and y is equal to j, we have the relations of q sub 8 are captured by q sub 8 is equal to this presentation where we have xy such that x to the fourth is equal to 1, x squared is equal to y squared. The inverse of y times x times y is equal to the inverse of x, right? So for q sub 8, we have I to the fourth is equal to 1, I squared is equal to j squared, which is equal to -1. And furthermore, we have y to the -1 times x times y is equal to j to the -1, which is times I times j, which is equal to -j times I times j is equal to negative, open parentheses, j I, close parentheses, times j, which is equal to negative, open parentheses, negative k, close parentheses, times j, which is equal to kj, which is equal to negative I, which is equal to the inverse of I, right? So yes, the inverse of y times x times y is equal to the inverse of x. That holds, okay? Now I'm going to look at something which is a bit peering ahead, but not too much so about this, which is that these relations force a normal form with at most 8 elements. And we haven't really exactly talked about what that means as like rigorously, but we'll get there. Just like keep this in mind, this whole idea of a normal form, and like just this is just sort of like an inkling of what we'll look at in the future. So 8 elements, 1 x squared, x cubed, y yx squared, yx cubed, and furthermore, the induced multiplication reproduces, ooh la la, the quaternion rules. So let's see. And that yields isomorphism. What's that? To q sub 8. So these are different sorts of notations for that. So there's a lot of notations which you could use for isomorphism. I think like some even like go like, okay, it's just an equal sign. It's like, oh my gosh. Okay, so those are the presentations of Q8, and I think that's it for 1.5. Happy to be corrected, of course, by either my future self or by a whole bunch of other people. And that is it for now.